In this video, we are going to talk about radioactivity. In 1896, Henry Becquerel noticed some spontaneous light, and this spontaneous emission of light is called phosphorescence. And spontaneous emission of light means that it will just give off light. Now, it has to be exposed or it has to be activated by the light. So there has to be some sort of energy going in there before it will go through this process of spontaneous emission. And this original phosphorescence discovery was the emission from uranium. And uranium contains unstable isotopes. When you have an unstable isotope, that isotope is going to do whatever it can in order to become more stable. Remember, unstable means higher energy, stable means lower energy. So it wants to get back down to that lower energy state. Mary Curie was the one who came up with the term radioactivity. So radioactivity is the name that's used for those uranium nuclei and the fact that they emitted those radioactive particles. Mary Curie even discovered radium and polonium and did a ton of work in radioactivity. So these unstable isotopes are going to do whatever they can in order to get more stable. We have what is called the band of stability or the belt of stability. And this is the non-reactive or non-radioactive naturally occurring isotopes. And these are all that there are. There are no other naturally stable isotopes that we know of right now. So each one of these little dots represent a stable, non-radioactive isotope. If you have an isotope that is not on this band of stability or this belt of stability, then it is going to be radioactive. And like I said, radioactive isotopes will make their way to the belt of stability, meaning they will either give off or absorb these radioactive particles. So let's look at the different radiation types. Background radiation is low levels of ionizing radiation, and these occur from natural sources. So you can see here we have artificial sources, medical procedures, nuclear medicine, and consumer products, industrial and occupational background radiation. And then we have naturally occurring sources. So space, soil, internal, these are all examples of background radiation that we can be exposed to on a just every single day. And then we also have radon and thorium. In this class, we are going to talk about three different types of radiation. So as these radioactive isotopes become more stable, they will give off different particles, radioactive particles, or energy to become more stable. So the first one we're going to talk about is an alpha particle. And an alpha particle, it contains two protons and two neutrons. So it's given the symbol helium with a 4 and a 2, or an alpha symbol with a 4 and a 2. So it contains two protons and two neutrons. That's why the mass number is 4. And the atomic number there is 2. So you can see it looks identical to a helium atom. So if you have a really, really big radioactive isotope, then it's going to give off alpha particles so that it can get more to a more stable isotope faster. These are the largest radioactive isotopes. They cannot travel very far through the air because they are so large. If you are exposed to them, they can cause skin burns or they can cause some damage to your skin, but they will not penetrate to the internal organs. So if you have exposure, um, it probably won't do any internal damage. You can actually protect yourself from alpha particles just by wearing heavy clothing, such as jeans or heavy cotton. Now, a particle is identical to an electron, and it is given the symbol beta with a 0 and a -1, or 0, -1, and a little e symbol similar to an electron. So it is identical to an electron. This is smaller than an alpha particle. And that makes sense because an electron is tiny compared to a proton or a neutron, and an alpha particle contains four total particles, or subatomic particles, two protons and two neutrons. Now, beta particles can penetrate into your flesh. However, the likelihood of them being able to penetrate so deeply to get to do any internal damage is low. You can protect yourself with heavier substances, such as like an iron apron or something of the sort. They can travel a lot further in the air because they are a lot lighter than an alpha particle. Now, a gamma ray, which is given the symbol gamma, oh, that does not look like gamma. There we go. Gamma 00 has no mass and no charge. It is not a particle. You can think of it as it is pure energy. It is a high energy photon. So a gamma ray can penetrate straight into your internal organs and cause damage. And you need very, very heavy substances to protect yourself against gamma rays. The ionizing power is the ability to ionize another molecule. Alpha particles are better at have a greater ionizing power than beta particles, which are going to be greater than gamma rays. The penetrating power talks about how far these different particles or these different radioactive materials can penetrate a material such as your skin and cause damage. Now, gamma rays are by far they have the highest penetrating power, followed by beta particles, and then finally alpha particles. Now we can predict the atom or the isotope that a radioactive isotope will become after they undergo the radiation. And we can do that using a nuclear equation. Now, this is very important. In a nuclear reaction, we never balance the atoms. In fact, the atoms will all be different. So we must balance the subatomic particles, which are the protons, neutrons, and electrons. So, in other words, we need to balance the mass of the reaction. And I like to think of that is instead of balancing the letters, I balance the numbers. So if uranium undergoes alpha decay, which is where it emits or it gives off an alpha particle, I need to make sure that all of my numbers match up. So I'm going to write out all of the elements and particles using isotopic notation with mass numbers and atomic numbers. The mass numbers on each side of the equation should match. So since I have 238 on my reactant side, an alpha particle has 4, then I can take 238 minus 4, which will give me 234. So I'm going to have 234 as my mass number for the isotope that I'm going to form. The atomic numbers on each side of the equation should also match. So we can solve for the atomic number, which will also give us the identity of the element that is being formed. I have an atomic number of 92 on my reactant side, and my alpha particle has an atomic number of 2. So if I take 92 minus 2, that is going to give me 90. Now I can look at my periodic table and figure out which element belongs with 90. So I have 234 over 90. And if I look at the periodic table, I can find the element that has an atomic number of 90, and that is thorium. So we identify the missing element or particle using the atomic number. In the second example, we have carbon 14, and it is giving off or it is emitting a beta particle. So I'm going to make sure that my mass numbers are equal and my atomic numbers are equal. Notice that a beta particle does not have an atomic number. So the atomic number should stay the same on both sides of the reaction. However, the number up top is going to change. A very common mistake I see with this type of a problem when we're dealing with beta particles is people will put a 13 right there. Don't write that down. It's not correct. Remember, 13 minus 1 equals 12, which is not equal to 14. So this number should actually be 15. And if we look at the periodic table, the element with the atomic number of 15 is phosphorus. In this example, the phosphorus is taking, oh, not phosphorus. Sorry about that. We have a mass number of 15 and we have carbon. There we go. Much better. I think I started looking at the next one. Now, phosphorus can take up a beta particle, and we want to do the exact same thing. Now, notice that our beta particle, again, does not have an atomic number, so my atomic number should not change, which means that the identity of my element shouldn't change. In order to calculate the mass number, I need to take my 33 minus 1, which is going to give me 32. So this would, phosphorus 33 will take on a beta particle and become phosphorus 32.